Okay, it's my pleasure to introduce Smaranda Muresan. Samara did her PhD at Columbia, and she's currently a postdoc at the University of Maryland. But I should put in a little plug for her, saying that her postdoc is ending this summer, and she's currently looking for a job. So if you're looking for a talented computational linguist, look no further. So Samara is going to talk to us today about her research interests in combining two things that are sometimes treated as separate in computational linguistics. The formal description of language, such as constraint-based grammar formalisms, and the problem of how you go about learning these things.
Thanks, Chris, for the introduction and for free advertising of the job market. So I'm going to talk today about learning constraint-based grammar from representative data, and this is actually a part of what I did in my thesis at Columbia. So just to show you a picture of what natural language processing looked in the 80s, the main focus there was actually how to get computers to do a deep processing of language. So for example, if you look at machine translation, the goal was actually to start from the source language, go out to an interlingua, and then come back to do a generation and then generate the target language. So you have here like a absolutely full semantic analysis in order to do that. So all this work was actually focusing on how you can develop, grammar formalism that combines syntax and semantics, use complex constructions, and also use like word knowledge. So the problem that even if you have deep understanding, the problem is that these methods were not scalable. So it's very hard to scale up. There were grammar formalism written by hand, and so the learning was not part of this picture. So you have deep semantic and syntax, but you don't have the learning. Now, if you look at the 90s and recent years, is actually this completely shift. So you have now scalable systems. So the focus on actually how to develop scalable system. You actually have some of the work in syntax and how can you learn syntax, but semantics is completely out of the picture. And if you look at the problem of machine translation, it's even like going more from like a string to string translation, not going to semantic, not talking about interlingua at all. So we have now a shallow but scalable system, but the semantic is not really part of the picture. So now what we actually want for a next generation semantic web, or if we want to actually bring more deeper semantic analysis in the natural language processing system. So what we have is actually we have a lot of textual data which contains complex linguistic phenomena, and also we have different domains and languages. And also we have ontologies, which actually can see as a model which can capture the meaning representation. So what we need is actually to have a deeper understanding of this text, dealing with semantic representation that actually assure tractability, and also to be able to learn them. So how we get this is actually bringing together syntax, semantics, and learning into the same framework. And this will be like deep and scalable. So there are two ways to get here. One is to get from the syntax and semantics and try to bring learning into the picture. And the other way is actually going from the learning and the more shallower approaches and try to bring semantic into the picture. In my thesis, I actually started from the first part where you try to get trying to get from the syntax and semantic and try to bring learning into the picture. And in recent work that I did in my postdoc in the context of machine translation, I'm going to the other direction. But in these talks, I'm actually talking about how can we build deeper language understanding models that capture syntax and semantics, but at the same time are learnable. So let's look at an example here. If you have the task of text-to-knowledge acquisition, and if you look, for example, in the medical domain, and you want to try to acquire terminological knowledge. So here are several examples of definitions that were automatically extracted from a corpus of consumer-oriented medical articles. And for example, if you look at the definition of hepatitis A and hepatitis B, the main difference between these two, one that actually differentiate between the two definitions, is that one, hepatitis A, is caused by a virus that does not depend, and the other one is caused by a virus that tends to depend persist in the blood serum. So you have negation. We have, for example, other complex phenomena like rising and control constructions. So starting with this definition, we actually want to try to get to a representation which capture all the semantic association between these concepts. So you can actually build a hierarchy of concepts saying that hepatitis A is a hepatitis and hepatitis is a disease and so on, but goes deeper than the ESA hierarchy. It's actually capture all the possible association between the concepts. And moreover, it not only deals with the concepts, but also with instances of concepts. For example, here, the difference is between, there are two instances of the word virus. One is that does not persist, and one is that persists, and this actually belongs to both of these different definitions. So once you have this kind of construction, also another important, why you want to get actually this semantic representation is that once you have built this such of representation, you also want to be able to query this representation using natural language text. So for example, if we want now to ask the questions, the two questions, one in blue and one in red, like what is caused by a virus that does not persist, and then the other one, what is caused by a virus that tends to persist or that persists, you represent the same style of graph representation, and you want to get actually precise answer at the concept level. So the first one should get you the concept for hepatitis A, and the second one for hepatitis B, and then you can also have the freedom of getting all the associated concept with this particular concept. So in order to be able to do this and actually learn, to automatically acquire this kind of representation, I introduced in my thesis a new grammar formalism, which I call it lexicalized well-founded grammars. And this formalism combines syntax and semantics, but at the same time is learnable. As a semantic representation, I use a shareable representation, which is an ontology query language. So defining the semantic, this grammar formalism, then the question is how you can actually learn this formalism. And I introduce a new relational learning model based on a small amount of annotated data, which I call representative example, and I'm going to tell about it. I also define the search space of learning this grammar as a complete grammar lattice, which actually assures that you all the times learn the same target grammar. And I give a learnability theorem. And I also implemented a practical framework for learning these grammars and in the text-to-knowledge acquisition and query task. So just give an example of kind of an architecture of this entire formalism is that you start first with these representative examples, which contains of strings and their semantic representation. So for example, a representative example for a noun phrase can be an adjective modified, a noun modified by an adjective, a determiner modified by, a noun modified by a determiner, and so on. And then you can also have a larger representative, a larger corpus which contains only weakly annotated example, which which is used for generalization purposes. So you have a learning model that learns a grammar, which, if you look, it has a context-free backbone, like in general grammars, but it also have the non-terminals are augmented with semantics, and we also have constraints at the grammar rule level. And I'm going to talk about the formalism in a short while. The constraints is actually make a connection to an ontology. So having this grammar, then given a text and the parsing, and the parser is actually you obtain the semantic representation, which is an ontology-based representation, and then you can use different task-specific interpretation in order to obtain knowledge and semantic analysis, and I'm going to talk about in the particular task I've done with using for the terminological knowledge acquisition.
Go a little slow, I'm getting lost here. So in the representative examples, you have strings, comma, something.
The semantic representation, right.
Tell me more about what it could be, because I'm not able to
I'm just going to talk about everything, how the grammar formalism is defined. I just want to give a big idea of what is actually the input. You have this kind of string as semantic representation, and you have a larger corpus that could be used for generalization, but I'm going to talk about what exactly this representation is.
Okay, so for the time being, I should just assume that the grammar will then include as its, I guess, as its tokens or its constituents, both word strings and semantics.
Right, yeah.
So that the notion of compositionality will say not just that a noun phrase and another adjective can be combined to get a bigger noun phrase, but in fact, a noun phrase with some semantics can be combined.
Right, exactly. So you can have the representation with the composition, both of the strings and the semantic representation of, for example, of a noun phrase is composed by the semantic representation of the parts.
So then there will also sort of be, so if I'm able to project this grammar, I can project it on the lexical side to get a standard lexical grammar.
Right.
But if I project it on the semantic side, there will actually be some rules of composition for
Right,
the
right, yeah,
Okay.
yeah. And I'm going to talk about what the compositionality,
Okay.
how the semantic compositionality goes. So I'm going to talk, the outline of the talk is that I'm going to introduce this formalism that I said that is able to actually learn syntax and semantic together, which is called lexicalized well-founded grammars. I'm going to present you the learning model and also how the semantic representation I'm using can be used for like deep language understanding. I'm going to present then a utility of the grammar learning model and then conclude with future work. So the grammar formalism in the 80s was defined definite closed grammar were introduced by Pereira and Warren in 80s, and then I chose this is actually a generic grammar formalism. It's not actually tied to any linguistic theory. And one advantage that this grammar formalism has is actually you can augment the non-terminals with any type of semantic representation or any type of representation you want. And also you have constraints at the rule level. So you can have to constraints the parsing and, for example, generation and so on. But the issue with this formalism is that it actually has Turing machine power, so this is undecidable. So in my thesis, starting from this definite closed grammar formalism, I defined this lexically well-founded grammars, which is a new type of definite closed grammars, which are decidable and learnable. So let me just describe a bit what the formalism is, and then I'm going to give example on all these like blue points, which actually make the formalism different from others, like context-free or like DCGs. So like in context-free, you actually have a set of finite terminal symbols. Then you have a set of elementary semantic molecules, which actually are this representation associated with the terminal symbols. We have a set of finite non-terminal symbols. We have a set of constraint production rule, and I'm going to describe what are these production rule. And then also we have a partial ordering relation among non-terminal. And this partial order, I'm going to just tell you that it will be useful for assuring the learnability of the formalism. And then we also have the start non-terminal symbol. So let me go in turn in each of these parts that are actually in blue. So for example, what is the finite set of elementary semantic molecules? So let's imagine we have an adjective. So the adjective is major. So the semantic representation associated with the adjective it contains two parts. One, which I call the head, the entire head, which is a flat feature structure. It contains information for composition. So for example, for an adjective, I'm saying that it is a category, which is an adjective, and also had like a variables which give what is the head of this, phrase. And the other part of the representation is the actual semantic representation, which is an ontology query language. And what it is actually a logical form which is composed of like atomic predicates, which are concept attribute concepts. So for example, if we look at what is actually the meaning of an adjective, it is a concept in an ontology, which is X1 is a major, which is like, it's a concept in ontology, but also it says that it's actually a property of another concept in this ontology. And this is given by the atomic predicate X2, which will be instantiated with a noun, point Y, it's equal X1. So given this semantic representation, we can see that actually this can be seen as an ontology query language. So the variables in this representation are actually concepts or slots in the ontology. So.
Excuse me, so X2 applied to Y is X1, is that what it said?
No, it's actually a concept attribute concept. If you think as a frame-based representation, so you have that the relation between X2 and X1 is given by Y.
Given by Y.
X2 is Y is X1. What would Y be here?
For example, here it will be.
I mean, Y is actually a constant name, right?
Yes, it's actually a
so
variable.
Every modifier has a Y.
Right. Yeah. Exactly.
What's
yeah.
the Y of the? I mean. What's the Y of this modifier?
So okay, so here, if you look here, for example, you say that this is that adjective is it's a concept in ontology major, right? And then what it means that this adjective major, the meaning is that it will be modified. So this y is actually the degree here. And then x2, it will be instantiated with, let's say that if we have the phrase major damage, this will be the one that x2 is becoming the noun.
So in other words, only nouns which take modifiers of the form y can take major as their modifier. So you're saying that somehow, is y, I'm not following whether y is just a placeholder or y
Place is a variable. Yeah, it can be instantiated with anything. I mean, the
Well,
only
it's
thing
not-
that...
Now I'm confused. Because you wrote concept.attribute. What fills in y?
In this case, the y it fills by the slot, the degree.
No,
So the relation
what
doesn't-
instantiates y? What causes y to be
Yeah, I'm
instantiated?
going to talk about it. This is actually instantiated in the grammar rule. I have it is constraint on the ontology that will instantiate that. So when I'm talking about the rule, I'm going to show exactly how this comes together, how the compositionality happens and how the interpretation
So
happens.
just read that line. How are we to read the line? X1
So
is a major.
x1 is a major. So this means that this part of the representation gives me that the major is a concept in an ontology.
Okay.
So you have...
What's the thing after the comma?
So the thing after the comma tells me that what is actually a meaning of an adjective. Meaning of an adjective, it is a property, value of a property of another concept, right? So if I say major, also let's say another example. If I say tall man, right? So what
You
is
say what?
tall man?
Tall man.
So what is the meaning of tall is that it is a concept in the ontology, but it also the value of a property, which is height, when associated with a noun, which in this case is man.
Okay.
So this is the way that to represent this is the way that how you actually represent the adjectives. So what is the meaning to how to represent the adjective?
So sorry, before you go on, I have an unrelated question. And if you're going to answer it later, then just say so. You've separated this structure into a top part and a bottom part, and you've labeled the top part information for composition. So I'm guessing that what you're doing is something like this. You could have incorporated the bottom part constraints into the top part, the way one would do in HPSG, and you chose to keep them separate. Because you're going to put some restrictions on the top part that ensure that things are decidable. The bottom part isn't going to, has to be written in such a way that it doesn't impose any constraints that can't be satisfied bottom up.
Right.
And the top part has to be, satisfy some restrictions in the grammar that prevent you from having to do anything Turing complete.
Right. Yeah, and then especially because you will see that actually the top part, it would be actually used as a compositional constraint, and it will be a path equation, which is like just one-step path equation. It will not be a...
And so you're not allowed to have any nesting, in other words,
Exactly.
in the top part, and that doesn't work.
Right. Yeah. Okay, so like more complex example here, if you have a sentence, again, the variables gives you pointers in the ontologies, and then, every word has actually a semantic representation, and it's the concept attribute concept representation. So then how can we get, the question that it was, how can you actually compose that? How can you actually get to compose major damage from the major and damage the representation? So the answer is through the constraints grammar rule. So if we look, for example, the rules which gives me an NP or an N given it's an adjective and a noun. So what is this rule saying? So what we have besides the context-free backbone, we actually have the strings, which, so for example, here we can say that, major damage, major and damage. So we have the strings associated, but we also have this semantic molecule, the semantic representation associated with that. So in this, so you have both for major damage, the adjective major and the noun damage. So now the question is, how can we, and so the association between, so then the non-terminals are augmented with the strings and the semantic representation. So what is actually this grammar producing? The language generated by the grammar will build this association between the strings and their semantic representation. It will not only be the strings. So now the question is how we actually compose. As you say, how can we compose major damage from major and damage? So the string is just concatenated. The semantic representation, again, are only just concatenation, and we apply a variable substitution to that. So, and then the heads are realized, and I'm not going into detail, this is described in my thesis, actually just the path equations, which is basically, you can see, is a unification on the heads of the parts. So this is the way that you actually instantiate, for example, and you can actually link, for example, here, that this x2 was actually linked, and now you have that variable x is x damage, and then, but still at this point, we do not have instantiated the variable y, so we don't know exactly what is the relation between major and damage. So in order to do...
As Jason said before, those are only path equations over the h part.
Yes, yes.
And that's not recursive.
Yeah, it's not recursive, yes.
And hold on, so let me make sure I understand this. So suppose I didn't see any of the stuff on the top. I'm just looking at those two items.
Right.
And I want to decide whether I can compose them or not. Then first of all, I need to have a rule on the upper part which says that I can take the category adj and the category noun and compose them to produce some category. Let's say in this
Right.
case n.
Right.
Furthermore, that in this case, if I do that, then this item called damage, a major, will in fact be the modifier of something. And then that something will be given by the grammar rule. So in this case, adj noun gives you noun phrase. So noun is the modified, if you will.
Right.
And then, because x2.y is x1, it will mean that major will semantically play the role of that modifier of damage. But
Right.
that is not required for the composition. All that is required is that whatever fills the place of x2 for major, permit an attribute.
Right,
And as
right,
long as it
right,
permitted an attribute, the attribute
Right.
that major...
And then this is actually will be used, and I'm going to talk about when I talk about the learning, because when you give the learning, so
Right.
let's say that I already have the rules for an adjective and the noun, and now what I'm given in the learning is that I'm actually given this as input. And I want to learn a rule, actually I want to learn this rule.
Right. No,
So-
before I learn the rule, I'm trying to figure out how the rules are used. Okay.
And okay, so and then after you have the composition, then the interpretation on the ontology is actually you take this, and then this will be instantiated from the ontology, and the variable y will get instantiated.
Okay, where did the green part come from is what I was asking before.
The green part can actually come from the ontology. Like if you have an ontology that says you the major and damage are related together, you query this in an ontology, which will have, let's say, this graph-based representation. If you already have, then it will give me degree. And if there are many relations, it can give me like all of the...
I see, okay. So do you get disjunction? Suppose damage can have a couple of different roles. You're saying that damage has a few roles and major has a few roles that it's able to fill. And you're looking for a role which is offered by damage and fillable by major.
Yeah.
Is that what
Right.
it is? Okay. So that's why y is underspecified here.
Right.
So now I have a couple of obvious questions. What happens if there are multiple such roles?
I mean, between the major and the damage.
Yes.
Right. I mean, you can actually give it...
And you get this all the time in noun-noun compounds.
In what?
You get this all the time in noun-noun compounds.
Right. So you
So
can
if I
actually...
say an Indian restaurant, do I mean that it serves Indian food, that it's run by Indians, or what?
Right.
That's right.
So I think in this case, right now, it's non-deterministic. So basically, you get all of them. So you can prefer, and then you can say, I prefer the first one, or if you try to model the ontology probabilistically, and then we'll say, you can have, it's more likely that I meant this, rather than I meant the other ones. But right now, you can actually have non-deterministically, it returns you all the filler, the slots.
Okay, so that was the first obvious question. What if there's two roles you can fill?
Right.
What if there's no roles you can fill? Because I thought you weren't allowing B to serve as
Yeah,
as
then it
constraints.
fails. This will fail.
Oh, okay. I thought you said that B was not serving as constraints on composition,
No.
but
This
only
will,
giving you interpretation. That's what I understood your previous slide to be.
right now, and then no, this will actually, and then this will actually fail. For example, if I have major birth or something that I completely cannot associate these two together, this will fail.
So why don't you end up getting, well, maybe it's still limited enough that you that you're not as powerful as HBSG.
Right. I mean, it's
Yeah, on the previous slide, you were pointing to the H part and saying that you were going to use that for your compatibility constraints
Right.
In order to prevent the computational power from being too great. But now you're saying that you also use B in conjunction with the ontology for compatibility constraints. Because you're not allowed to put major together with bird.
Right. I mean, you do, but you actually only can have. I'm using this actually natural language. You can see it as a natural language as a problem formulation. So I'm not doing a lot of inferences, because if you start to do a lot of inferences, then it's just, you can actually get intractable. So I'm not, you can fail and you can look at measure and damage. There is no association between that, and then it will fail. It's a direct link, for example.
Okay, I'm guessing that what you're saying is that the particular kind of things that can end up blocking this
Right.
are computationally modest,
Right.
which I believe from this example, but I just don't see, if you wrote more complicated things in the B sections, where that would take you.
Right, and then, I mean...
Because you can write arbitrary unification equations that go to any depth there, right?
Right, I mean, yeah, but I think it's also like when you look and how can you actually search the ontology for finding this, you can define more like tractable or less tractable, but it's not, I didn't focus on exactly on that part, but seeing this as actually don't doing a lot of inferences, I think this is actually what gives the tractability of when you do the parsing for this. For the
Okay,
formalism.
well, I'll take your word for it.
Okay.
Then the third obvious question, and I hope this isn't taking too much time, is what happens if the degree role is already filled by a different adjective?
I'm not sure, because all the time when you
Suppose you say major severe or major irreparable damage. Maybe irreparable isn't the degree role, but suppose you say major severe damage or something.
Why don't we let her go? I don't think this is a
okay.
major question.
No, but you can actually have different, you can have different roles for different things, and then it all the times gives you the role that connects these two particular one. It doesn't look at if it connects already with the other one. I mean, if irreparable damage, you can have one role, and then major, it's also connected with the other one.
Let's take it offline, as Bob said.
Okay, and then the third part, which makes actually the formalism learnable, is that you actually have a partial order among non-terminals. So if we want to see this, actually, it's similar with the idea of stratified logic programs. So what it means, you have actually a partial order. It either the non-terminal in the left-hand side is greater than the non-terminal in the right-hand side, or the arguments, which is the syntagmas, are bigger. And this I showed in my thesis. I'm not going to have time to talk more detail in here. This actually allows the parsing termination and the decidability of this formalism, and also allows to define the representative examples and to define the search space for grammar induction as a complete grammar lattice, which will allow us to give the learnability theorem. So as I mentioned before, the language generated by these grammars are not only strings, but are also strings together with their semantic representations. So now that I briefly talk about how the grammar formalism is, I'm going to show how we can actually learn the grammar from examples. And just to give you like the learnability theorem at the beginning, just to give an idea what I try to accomplish with this learnability theorem is that given the set of representative examples and then the set of representative sublanguage, which are more general examples used for generalization, because the search space is defined as a complete grammar lattice, this will guarantee that all the time we actually end up learning the top element of this grammar lattice. And then I'm going to talk about what is the learning model and how can we actually get to this learnability theorem. So what are the requirements for learning in this case? We need to learn structures, we need to use relational representation, and also we need to use background knowledge. So the model that I use for learning is inductive logic programming. So inductive logic programming was defined in '94 by Kitts and Derowski. It was used before, but this is the formalization I'm using, is that you have a correct probability relation for a first order logic. You have a background knowledge, B, and a set of positive and negative examples. And also you have a hypothesis language. So what you need to find a hypothesis such that together with the background knowledge, this hypothesis explains all the positive examples and doesn't explain any of the negative examples. So this tuple of correct probability relation, the background knowledge, examples, and the hypothesis, it's called the inductive logic programming learning problem. So So the way I approach induction of this lexicalized well-founded grammar is actually to look at the inductive logic programming as a decidable inductive logic programming problem. So now I'm going to talk in turn about which of these elements of the tuple of the inductive logic programming is appropriate in our model. So the background knowledge contains of the set of the grammar rules already learned. You have the lexicon, which is these strings with their semantic molecule, which are ground atoms, and also we have a robust parser as an innate inference engine. The examples, we only have positive examples, so we have these representative examples where we generate the rules, and then we have a representative sublanguage will be used for generalization.
I don't know what the adjective representative means. That means you like them, or what does it mean, representative?
So it's actually the simplest syntagma that can be generated by the grammar. So actually in my thesis I define it formally what it actually means, but the idea is actually the building blocks for the simplest syntagma that you can generate from a grammar rule. So for example, if you have for a noun phrase, the simplest one, you get an adjective and a noun, or a determiner and a noun. And then the representative sublanguage for this particular one will be like a noun modified by a recursive number of adjective or so on. So it's more complex one. But the representative are the simplest syntagma that you can actually generate from a grammar rule.
I thought we get that from the world, and then we induce the grammar.
Right, so
In
this
other
is the...
words, our environment, books, not...
Right, so you can see, if you think about, so this is like theoretical way of like thinking how they are connected to the grammar, but then in the learning set, this is what you do. You give these examples and then you learn the grammar.
But does the word representative restrict the examples that you give from which you induce the grammar?
Right, so I will talk about later, I mean, you can have different algorithm design. One, we actually give the representative, the user basically give the representative example to the learner and then use this representative language to generalize. And then in this case, what is important here, the representative examples are needs to be semantically annotated. And the larger corpus needs to be weakly annotated or unannotated for generalization purposes. If we don't know which are the representative example in the larger corpus, then you need to have semantic annotation for the entire one because you don't know exactly, so you need to learn the structure as well. So then the trade-off there is actually you will need to have the whole annotated.
So there is judgment involved in deciding.
Right.
All right.
Yeah. So the probability relation is the robust parsing, and I think there's a parsing as deduction, and then what it says is actually that the parsing of given the background knowledge and the current hypothesis, we are able to parse the representative sublanguage. So now I'm not gonna have time to talk about in detail about this hypothesis page, but what I want to mention here that the hypothesis language in this particular problem is formed by these grammars, lexicalized well-founded grammars. But in my thesis, I showed that a subspace of this space is form a complete grammar lattice. And this will be important in order to prove the learnability theorem. So this was there are some properties, in order to do that, there are some properties that are adapted from the work that I've done in learning logic programs. And one of them I already talked, it's actually this partial ordering among non-terminals. There is a data flow coherence constraints between the arguments and also this idea of having representative examples. A new property that is particular for this grammar formalism and it will help actually defining this lattice of grammars is that it contains only the grammars that are able to parse the representative example, and I call this representative example parsing property. So all the grammars in this lattice are able to parse the representative examples. And I'm not going to enter into detail. And another property that needs to be done to do the learnability theorem is that the representative sublanguage needs to be conformal with the lattice top element. And what I mean by this is that if you look at the lattice, and then if you take any two grammars in which one is more specific than another grammar, then the number of examples generated by this grammar should be less. If you look at the numbers of examples that this grammar can parse from the representative sublanguage is less than the one that from the more general grammar. So given all these properties, the grammar I define a new model for learning, which is grammar approximation by representative sublanguage, which says that given the representative examples and the finite representative sublanguage, it learns a grammar which is unique and who can actually generate all the representative sublanguage. And I give the learnability theorem that I mentioned before. So now let me give you, okay, so before that, so as I mentioned before, we can design actually different type of algorithm in order to learn this grammar. So one is if we have the learning from an ordered set of examples, then we actually end up doing bottom-up learning directly, and the hypothesis space is a Boolean algebra. So what it means by order, for example, we know that we need to learn adjective before we need to learn the nouns and so on. But this is actually very cumbersome if you really want to model, because you don't know exactly what phenomena are coming before what phenomena. Then I define an algorithm which actually learns from an unordered set of examples. You don't need to learn the order. And then I define an iterative algorithm which actually converges to the same grammar because of the property of the search space. And then it comes the question why, if you don't know the representative example, what happens? And then you can define another algorithm which actually will converge to the complete grammar lattice search space. And it's also learn the same grammar, but then in this case the trade-off, it's in if you really want to annotate more data because you don't know exactly which are the representative example. So just to give a concrete example, let's say that we have in the background knowledge an adjective, for example, the rules for an adjective which is major, we have a noun which is damage, and we already have the rules learned, which, for example, A, it's an adjective, or A, it's an adverb, and an A, which this actually is a rule for saying that adjectives can be modified recursively by as many adverbs. You have an N, which is a noun, and so on, other rules for the nouns. And now we have the current example. Okay, sorry, this was supposed to be bigger. So we have the lexicon, and then we also have the previously learned constraint rules. So now we are in the current representative example right now. Given this background knowledge, we want to learn the rule. If we see this example, an adjective, a noun modified by an adjective, and we have the semantic representation where we have the feature structure which gives the category, and we have the semantic representation as well. So having this example, the first step is to generate the most specific constraint rule from that. So how this rule is formed is actually you look, and the left-hand side non-terminal is given by the category which is given in the representative example. So we have that like this will be an N, and then the most specific rule that you get from here is an adjective a noun modified by an adjective and a noun, and you also run the constraint rule. So now, having this more specific rule, we try to generalize, and we generate a set of candidate hypotheses, which will be like more general. And then the way that we are choosing which of these rules are chosen in order to be the final rule is actually we try to take individual if of the candidate rule together with the grammar already learned, and we try to see how many of these representative sublanguage are passed. The one that gives you the most example covered is the one that is chosen, in this case an A, which is a recursive rule. And then this rule is added to the background knowledge, and then process continues iteratively covering all other rules. So now, if we have already learned the grammar, and define the formalism learning of the grammar.
Just a quick
Sure.
So you add both the course rule and the detailed rule to your, what gets added to the background knowledge? Only the best rule, or?
The best rule.
Okay,
Yeah.
not the ones that you developed on the way to.
No, it's only the best rule. Yeah. And then what I want to mention here is what is called actually the approximation by representative sublanguage, is that, for example, if I don't have, I'm not sure which one it is, loud, clear noise. For example, if I don't have this example, then these two, rule R2 and R3, will give me the same number of coverts. So the ties, I choose the most specific one. I don't generalize if I don't have evidence from the corpus that I can generalize.
In this case, you need to see a noun with a double adjective before you're willing to accept it.
Right. Okay, so now I'm going to talk briefly about how to do like deep, how I see like actually doing like deep language understanding with the particular, why is the semantic representation useful for that. So in doing this, as I mentioned before, and also not entering into tractability issue, I'm seeing natural language actually as a problem formulation. So it's not as a problem solving. So if I'm giving a puzzle, I can formulate it in natural language. I don't try to solve it. So I'm seeing meaning as actually text together with all the question and answer you can actually ask to this particular text. So I can see the meaning actually contained in a sort of representation. Then if you can actually get all the precise concept level answer to all the questions that you can possibly ask to that particular utterance. So for example, if you look here, who persuaded the doctor to examine us, we have all the question, and then the particular concept level answer. So we'd have to deal with complex question in natural language question, and we want to get answer at the concept level. So the representation are, as I showed before, we have the utterance level representation, which is obtained by the parser. And then, as you see,
Could you go back?
Sure.
Why is the answer to what did we do persuaded? Why is the answer what did we do persuaded the doctor? What does persuaded mean?
Right. So
if it doesn't have an object of persuasion.
Right. So here, what I meant is not actually the word per se, but is the concept that corresponds to it. So, for example, if you look here, I'm just going to show you. Okay. So let's say that I gave it's persuade, and then actually I can retrieve the concept, but I also can retrieve the whole context of that particular concept. So I can say here persuade, and it will be examine and doctor and stuff. So you can actually see the relations, what it is with this particular concept. But what I say is actually you retrieve the particular node in the representation. So we have the utterance level, which is given by the parser, which you saw the representation is a logical form. And then at the text level, the only thing that happens is actually this utterance, the semantic representation are actually asserted, so all the variables become constant. And then, so at this point we have reversibility because the grammar is reversible. And now, after this text level representation, we want to get an ontology level representation, which is this direct acyclic graph, which the property that this graph have is that it is the concept identity. So this means that there is a bijection between the node in the graph and the referent in the reality. So if we want to do, for example, an aphora resolution or something, you want to say that John and he, and so you want actually to say that all of them actually go to the same vertex in the representation, in the knowledge representation. So what does actually this give us is actually we can see this, the concept identity give us a logical equivalence seen as a concept identity. So, so what I mean by this, for example, you can say that two sentences are equivalent if they actually give the same answer to the same question that they are asked. And two questions are equivalent if they give the same answer with respect to the particular sentence. So let's look here, for example, Kim has not been reading the book. So if you take the entire representation and you want to say that it is a progressive, it's perfect, the tense is present, there is a negation, and the agent is Kim and the theme is book. And now we put both the question, who has not been reading the book? And then you actually have the same, you get the representation of that, and then in this case, this meaning, you get the answer, which is, Kim. But let's now say that we do not care in a particular context, that we are not caring about, we want to model the perspective and progressive and perfect, of the verb. And then in that case, if I ask the question, who does not read the book, it will give me the same answer because they will not have represented, the blue part will be removed from the representation and I get. So this, depending on how you want to get the particular task, you want to be more expressive or less, so we want to capture more, you can actually get sort of what is the meaning of. And then the same if you look, for example, if I want to say that an active and a passive voice is equivalent, for example, if I actually capture that it's a representation as that this is a passive voice, if I ask the question who has not been reading the book, that I don't get the answer, but if I don't represent the passive voice, then I get the same answer, and I say that the active and the passive actually are the same. So now the utility of the grammar we did, so I did a qualitative evaluation of this. I started with around 150 representative examples which were fully annotated, and around like 500 weakly annotated data. And also we need to give lexical categories for that, an elementary semantic molecule, for example, for part of speech. And we learn a grammar which around like 150 complex words, which are both left and right recursive, and you have also the compositional constraints, and evaluated on around 1,000 complex utterances. And what I followed here is actually to see if we can capture linguistic phenomena, complex linguistic phenomena, and also the task of terminological knowledge acquisition. So I described this actually, the whole qualitative evaluation in my thesis, and the type of phenomena I focused, it was on non-compounds nominalization, complex verbal construction where you can actually model the tense, the aspect, the negation, the finite and non-finite, rising and control long-distance dependency. And for example, the one complex example, you can see here, it's like an embedded number of relative clauses. And you can also ask questions. What does the president seems to try to get from the farmer? This is like a long-distance dependency. And okay, so and here, for example, this sentence is ambiguous. So in the semantic representation, you actually will get both the representation. One will actually have the illegally modifies get, and then the other one illegally modifies grew. And but then if you ask the question, how does the president seems to try to get royalties, it only for the first representation you will get an answer, not from the second one. And then for the terminological knowledge acquisition, this was done in a context of a medical domain. And I developed one system that actually goes using a more shallower procedure to extract definition automatically from consumer-oriented medical articles, and then using this as an input to build a terminological knowledge base from these definitions. So these definitions were automatically extracted. I use actually the lexicon from UMLS, which is a medical ontology, and the COMLEX, which is a generic ontology, because dealing with consumer-oriented text is more, it doesn't contain all the medical strict technical terminology, also general vocabulary. And I use a weak ontological model, which it only focuses on thematic roles and prepositions from the LCS database developed at Maryland, and adjective and attributes from WordNet. So I did a small acquisition and querying experiments. So what I actually tried to look at is how much the ontology helps, and then if you don't use the ontology, we obtain approximately 2.5 parses per definition in the case of acquisition, and then with ontology we have 2 per definition. Sometimes these were actually valid ambiguities, sometimes it's actually invalid ambiguities, but what we did is actually to enhance the semantic interpreter to let the user choose which is the one, and then we present actually not the semantic representation that was given by the parser, by this more graphic representation which was easier to look at and to populate the knowledge base. And then we did the same with the query. We use like 29 questions, precise and vague. We can actually, for example, ask, I have an example later what is actually a vague question. And the questions type were at this point, or who did what to whom, so it was only concerning the arguments of the verb. And here we also, the reduction in ambiguity per question is even more. So here is the example I presented at the beginning, and then the type of question. For example, we can have what is caused by a virus that tends to persist in the blood serum, as I said before, but also like this vague question, what is caused by something that does not persist in the blood serum, where the something will actually be a variable and it will be matched. And then, so this idea is that, it's useful for sometimes when you want to try to get all the relations that are existing between concepts. So what are the advantages, just briefly, is that you can actually answer questions relevant to particular instances of concepts. You have semantic equivalence between some syntactic forms, active and passive voice, reduce relative clauses, and passive and active construction involving rising verb, and so on. I'm not going to have time to talk here, but I did in my thesis, actually working on the merging of definitions, because sometimes you can actually extract from a corpus, you can have for a term alternative many definitions, and how can you actually merge them together. So in this case, I took advantage of the concept instance. In a terminological case, it's actually a concept, and definition I see as a naming of a concept instance. So, this can be seen as the first step on starting from a lexicon to develop a practical ontology. So as a conclusion, in the part that I described, it was part of my thesis, I introduced a new grammar formalism that captures syntax and semantics and provide access to meaning. a new semantic representation, which can be seen as an ontology query language. And also this grammar formalism is learnable. And I've presented a grammar model that learn efficiently these grammars from a small set of representative examples, prove that the search space is a complete grammar lattice or a Boolean algebra, and this actually can let us give a learnability theorem. So the theoretical conclusion, which of course needs to be practically, but if natural language can be covered by this formalism, then natural language can be learned. And also a new framework for induction of these grammars in the direct text-to-knowledge acquisition. So now just briefly, just one slide, and kind of the idea that I'm trying to use this in a machine translation framework. We are working in using kind of word lattices to include alternative verbalization of the same source language and use this in the machine translation. So we just submitted a proposal with Philip and try to look, and if you can take advantage of this formalism, because it's a reversible formalism starting with representation, kind of to generate alternative verbalization of the same input and then use this in a standard statistical machine translation framework. So now future directions that I'm going to focus is that right now the ontology, as I said, it gives you either these two words are associated or not, it can fail, but now it's like the idea is that can we actually model probabilistic deontology? Can you say that is more or less likely to be associated together, and kind of introduce this notion of probabilistic? And then develop learning and parsing algorithm that will actually be able to deal both with hard and soft constraints. Another aspect of the work is that actually to bootstrap the grammar on the ontology. So right now you can start with an ontology, learn a grammar, but then you can parse more text, and then you learn more construction, update the ontology, and kind of do a bootstrapping for the... And another interesting application that I'm interested in actually merging ontology via text. So for example, if I give a definition to one ontology and I give a definition to the other ontology, and then this will actually return me the same concepts, or like we can see how we can actually define this matching. There I can say that these two concepts can be aligned in the two ontologies. So after, these techniques will lead actually to a broader coverage using this formalism of different corpora in different domains. And as part of application, one is actually to go and do automatic population of knowledge bases from text. Right now I focus on terminological knowledge, but then to go to factual knowledge, you need to see how can you interpret temporal relation, how you deal with individual, and so it's more, more work to be done, and interested to work on various domains. Another point is actually I'm trying to looking at grammar induction for low-density languages, because you don't have a lot of resources. Starting to learn from a smaller amount of data is actually important. So I'm looking to see how can this grammar induction framework can be used for that. And in the machine translation, one aspect is the one that I sent, kind of to use this grammar formalism to generate alternative verbalization and to be used in a standard empty system. And also to focus on this low-density case where you don't have a lot of parallel data and you want to leverage that using only like smaller amount of data. And another one is actually to use automatic measure based on this, because this formalism gives you semantic representation. Instead of using n-gram matching, kind of to use more like a representation of the meaning through this graph algorithm. So thank you. Questions?
First of all, congratulations on finishing, despite all the questions ahead of time.
Okay.
Nobody's ever done it.
That's not true.
So I have a question for applying semantics in the machine translation. So you said, do you just use the semantic information to do previous sets of the source sentence, then you get the natives? So that's one way, right? So the other way, actually, because like Hara is just, is a parsing-based machine translation system. Do you actually use the grammar, during the decoding?
Right, yeah, so I think, so the one that I said is actually, this was kind of a first step that would be like kind of a short term, but yeah, in general, actually can use this format, because also have the reversibility property. You can actually see that even you can go to like learning grammar for the two languages, and then you get the semantic, and then you kind of do semantic transfer, and it can be like a different way of kind of including the...
So for the second case, do you have efficient algorithm to do this?
Well,
Like parallel parsing is very expensive if you want to add semantics.
right. I mean, right now the parsing is also like it's cubing in time. So yeah, I need to like I need to figure out and exactly use it and how to use it, and in order to do that, I haven't think about exactly how to actually include it during the decoding.
So I've got a clarification question. So what was the property of your grammar that made it learnable, whereas the definite clause grammar was not?
Right, so I think it's a combination of both, like what semantic representation you use. I mean, so representation is actually, you need, like, you have flat feature structure, you have the flat representation, and also the partial ordering among non-terminals that allows you to, so this is actually, these are the two, I can say, the two main points. That you also cannot derive the empty string, which is, and then you don't have cycles in the grammar.
Any remaining questions?
I know I had one, but I can't think of it.
Under specified question, I cannot give you an answer.
Oh, yeah.
Or I can give you many answers.
You can give it all.
I can give all the answer I can.